Hi guys, and welcome to this virtual lecture course on Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture we'll be discussing the four-vector formalism in special relativity. Four vectors are objects which live in four-dimensional spacetime. That's 3 plus 1 dimensions, 3 of space and 1 of time, and they transform under the full symmetry operations of the Poincare group. This means they transform under translations and rotations of our coordinate system, as well as the Lorentz transformations. Compare this to regular 3 vectors which live in three-dimensional Euclidean space. Vectors are things which transform under rotations and translations of our coordinate system. When we go to 4-dimensional spacetime, we can generalize this. We have to include then the Lorentz transformations which mix up space and time. We'll be discussing different kinds of 4 vectors in this lecture. We know of one already, the spacetime event. This is specified by 4 coordinates, 3 of space and 1 of time. We see that this of course transforms according to the Lorentz transformation. But there are a whole family of these, and we'll be discussing how to derive different 4 vectors in this lecture, including, for example, the 4 velocity, the 4 momentum, the 4 acceleration, and so on. This will set the scene for relativistic mechanics, which we'll be discussing in the future lectures. We'll see that there are certain objects which are relativistically invariant and are the same in all reference frames, and this is very naturally and nicely explained within this 4-vector formalism. In particular, we'll see that there are 2 different flavors of 4 vectors, the covariant and the contravariant 4 vectors. We'll be discussing both of these and their interpretation, as well as how they're connected through the Minkowski metric tensor, which encodes the hyperbolic geometry of the underlying 4-dimensional spacetime. So in this lecture, we'll be discussing a lot of the formalism. We'll be discussing a lot of the notation, for example, Einstein's summation notation and these contravariant and covariant 4 vectors and contractions of those objects. So this will allow you to then go to the books and other lectures and so on and understand how to read these equations. How do you read a relativistic Lagrangian that's manifestly covariant, for example? We'll touch upon an example of electromagnetism at the end of this lecture as a concrete example. So we'll be discussing this in the lecture. We'll be making an outlook towards relativistic mechanics. So let's get down to work. In this lecture, I'll be giving an introduction to 4 vectors as they appear in special relativity. Of course, this can be generalized even further when we consider general relativity, but that won't be within the scope of this course. An event in spacetime is specified by 3 spatial coordinates and 1 time coordinate. We can assemble these together into what's called a contravariant 4-vector. This is denoted by a capital X and a superscript mu, the Greek letter mu there. This superscript is referred to as the index, and what we'll be discussing here is called the index notation. By convention, when we use a Greek letter, such as mu, for the index, this means it runs over the 4 spacetime coordinates, 3 for space and 1 of time. The index mu can take values 0, 1, 2, or 3. So there's 4 coordinates, but by convention, we start labelling from 0. So 0, 1, 2, and 3. The 0th component is time, and the 1, 2, and 3 components are the spatial coordinates x, y, and z. So we can specify a specific component of our 4-vector simply by specifying the value of this index. X superscript 0, for example, refers to the time-like component, ct, whereas x1 refers to x, x2 refers to y, x3 refers to z. All of these things lumped together is referred to as our x mu, our 4-vector. And a 4-vector corresponding to a spacetime event is called the 4-position. Just remember that when you see the superscripts 0, 1, 2, and 3 here, these are not powers. So for example, x2 here does not mean x squared, it means the y component of the 4-vector. Since the x, y, and z components, labelled 1, 2, and 3, represent the spatial coordinates, sometimes we refer to the 4 vectors in this form, where we single out the time component in the 0 slot, and then we have a regular 3-vector corresponding to the spatial coordinates. I'll refer to these as time-like and space-like because, as we'll see, when we generalize to other kinds of 4 vectors, we will still have 4 components, but they won't simply be t, x, y, z, they'll be other things. However, we can still identify these as being time-like or space-like components. By convention, if we have an index which is a Greek letter, such as mu, as I've given here, this runs over the 4 components of the 4 vector. If, however, I use a Latin index, like I or j, then by convention this only refers to the space-like components, x, y, z in this case. From the contravariant 4 vector, we can obtain the corresponding covariant 4 vector by acting on it with the metric tensor of the space. The covariant 4 vector follows from this equation. On the right-hand side, we have the corresponding contravariant 4 vector, x nu, so I'm specifying this by the Greek letter nu here. And we're multiplying it by the metric tensor g mu nu. This is a tensor because it has 2 indices, and you see they're both subscripts, they're lower indices. Then we simply sum over the values of nu. Because nu is a Greek letter, as I mentioned, that means it runs over the 4 dimensions of spacetime, meaning we sum over the 4 components nu equals 0, 1, 2, and 3. Nu, therefore, is contracted in this equation. We get rid of the nu because we're summing over it. What we're left with is something involving mu, and that's what we see on the left-hand side. When you've seen these equations a few times, you'll get used to this. The idea is we sum over the value of nu here, and we're left with a mu. The mu is downstairs, and so it appears downstairs on the left-hand side of the equation. And x with this lower index, mu, is the covariant 4 vector. We refer to the contravariant 4 vectors as having an upper index, and the covariant 4 vectors as having a lower index. Is the Greek letter upstairs or downstairs? That's the thing which symbolically distinguishes between the contravariant and covariant 4 vectors. G mu nu is the metric tensor which defines the geometry of the underlying space and our coordinate system. We discussed the concepts of the metric tensor and what they mean in one of the first lectures of this course. And I'll say some more about what that means in special relativity very shortly. But first, let me introduce the so-called Einstein summation convention. According to Einstein's summation convention, we can write this sum here in this rather simplified form. We just leave out the summation sign. We just write g mu nu and x superscript nu, and the summation over nu is actually implied by the notation. Specifically, there's an implicit sum over repeated Greek indices where one of them is lower and one of them is upper. What do I mean? Well, in this expression, we see that nu, the Greek letter nu, is repeated in these 2 terms. And, furthermore, one of the indices is in the lower position and one of them is in the upper position. If we ever see something like that, then Einstein's summation convention tells us that we should just implicitly sum over the values of nu, which means, in practice, nu equals 0, 1, 2, and 3. This is referred to as contracting the 4 vector. So these 2 expressions are identical. This is literally just a notation. There's no physics in here, there's no mathematics, it's literally just a matter of notation. Whenever you see this thing, it means this sum. However, we'll see that using this notation cleans up and tidies up our equations hugely and makes things look very nice and simple. Einstein once joked that introducing this summation convention was his greatest contribution to physics. In the end, it just makes the equations look nicer, but you should always bear in mind that when we see things like this, there's an implicit sum. This operation, multiplying a contravariant 4 vector by the metric tensor and contracting this index, which means summing over this index, one upper and one lower, is referred to as lowering the index. And you can see why that is. You start off with a contravariant 4 vector with the index in the upper position, and you end up with a covariant 4 vector with the index in the lower position. So we can talk about lowering the index, and as I'll show you in a moment, we can do the inverse and raise the index. We can take a covariant 4 vector and transform it into a contravariant 4 vector. That would be referred to as raising the index. As a mnemonic rule of thumb, you can imagine these indices kind of cancelling. Imagine that we have one upstairs nu and one downstairs nu. We can sort of draw a line through these things, cancel them out, and then what you're left with is a mu downstairs, which is what appears on the left-hand side of the equation. However, I want to emphasize that this is only a mnemonic, it's only a way of remembering and figuring out what goes on in these equations. It's not really that we're cancelling these things. As you can see, there's actually a sum over mu here. But this is certainly a good way of remembering the result. The full theory of the way this works is actually part of the mathematical field of differential geometry, and this involves tangent vectors and fibre bundles and manifolds and so on, and all of this stuff. We won't actually get into that in this course. Maybe I'll do a lecture in future when we talk about general relativity, in which we'll go into the mathematical details more fully. However, in special relativity, we'll see that this is actually rather simple, and we don't need to get into all of that detail. So we've just seen that if we have the contravariant for position, x nu, then we can lower the index and obtain a covariant for vector x mu by doing this contraction, where the Einstein summation convention over the Greek letter nu here is implied. G with the two lower Greek indices, mu and nu, is the covariant metric tensor. It's the metric tensor that, when contracted with a contravariant 4 vector, gives the covariant 4 vector. On the other hand, when we're raising the index, as in the second equation, we take a covariant 4 vector and contract it with the contravariant metric tensor to give a contravariant 4 vector. So what is the relationship between these two different metric tensors? Well, we can actually find the relationship by first lowering the index and then raising it again. That returns our contravariant 4 vector back to a contravariant 4 vector. In this first part here, we are lowering the index of the contravariant 4 vector x mu to obtain x nu. Then we raise the index again to obtain x sigma this time. So by comparing the left-hand side of the equation and the right-hand side of the equation, we see that the product of the covariant metric tensor and the contravariant metric tensor is actually the identity matrix, and therefore the contravariant and covariant metric tensors are actually the inverse of each other. We see that they must be the inverse of each other because we can lower and raise the index and get back to where we started. In terms of the index notation, we can take this product with the Einstein summation convention implied here, where we're summing over the 4 values that the index nu can take here, which is repeated, 1 upper, 1 lower, and we obtain the identity matrix. This might look a little bit funny. We're specifying here 2 indices. Again, 1 is upper and 1 is lower. That's what you get after you contract the nu in this expression. So just as if you were to have 2 matrices, if you multiply a matrix by its inverse, you get the identity matrix. This is something very similar here in index notation. So far, all of this is very general, and here we have a totally general metric tensor for an arbitrary geometry of our space-time in an arbitrary coordinate system. Let's now be a little more specific and use the actual metric tensor that applies in Einstein's theory of special relativity in Cartesian coordinates. In special relativity, we use flat Minkowski spacetime. This is the geometry of 4-dimensional spacetime that we've been discussing so far in this lecture course. If we were to go to general relativity, we'd see that spacetime could be curved, but that's beyond the scope of this course. So here, we're just going to concentrate on the special case arising in flat Minkowski spacetime in special relativity. In that case, the generic metric tensor G mu nu becomes a specific metric tensor, the so-called Minkowski metric tensor, given by this eta mu nu. Traditionally, this is given by the letter eta, another Greek letter, I'm afraid. For our purpose here, we can consider the Minkowski metric tensor simply to be a 4x4 matrix. This is a bit of an oversimplification of the full theory, but it suits our purposes here. So we can regard the metric tensor as a matrix. Let's call it eta matrix. I'll denote matrices in this lecture with this double line underneath. And an element of that matrix, eta subscripts mu nu, is simply an element of this matrix. In particular, eta mu nu corresponds to the muth row and the nuth column. In special relativity, this takes the special form where the eta matrix is this diagonal symmetric matrix with ones or minus ones on the diagonal. Since we specify an element using mu and nu, which both run over the values 0, 1, 2, and 3, we can label the rows and columns of this matrix 0, 1, 2, and 3, 0, 1, 2, and 3, so that we can identify that the 0, 0th element is plus 1, whereas the 1, 1, 2, 2, or 3, 3 elements are all minus 1. All the off-diagonal elements are just 0. We saw this same object appear when we were talking about the matrix formulation of special relativity in a previous lecture. As you know, the metric tensor encodes the geometry of the underlying space. In this case, this Minkowski metric tensor encodes a hyperbolic geometry of the four-dimensional spacetime, as we discussed previously. We say that the signature of the metric is plus, minus, minus, minus. We're basically just reading off the values on the diagonal of this matrix. So we have plus 1, minus 1, minus 1, minus 1. This is referred to as the signature of the metric. I should mention here that there are different conventions about this. It is also possible to define the Minkowski metric in terms of the minus of this object. That would have a signature minus plus plus plus. This is also perfectly valid. You get exactly the same results when you compute any physical properties. It's simply a convention. However, we have to pick one convention and then stick with it. And in these lectures, I'm choosing the signature plus, minus, 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 which corresponds to this specific form of the Minkowski metric tensor. But just bear in mind that in other lectures or other books, you might see the opposite convention. Now, it turns out that the fact that this metric tensor is a diagonal matrix with just plus or minus ones on the diagonal makes things a lot more simple, as we'll see now. Firstly, because we have a diagonal matrix, it actually doesn't matter whether we specify mu or nu as the row or column, so we can be a little bit careless about this. We don't have to worry too much about whether the first index corresponds to the rows or the second index corresponds to the columns. It's a symmetric matrix. Furthermore, because of the special properties of this matrix, the contravariant and covariant metric tensors are actually identical. I mentioned earlier that they are the inverse of each other, and you can see because this matrix just is a diagonal matrix with plus or minus ones, clearly the matrix is its own inverse. So again, this simplifies matters in special relativity. Finally, because this is a diagonal matrix, it makes matters rather more easy when we're doing index contractions. As an important example, let's work out the covariant 4 position from the contravariant 4 position using this Minkowski metric tensor in special relativity. So we start out with the definition of lowering the index of our contravariant 4 vector. Remember that because we have this repeated Greek index nu, one upper and one lower, this, by the Einstein summation convention, implies this sum over nu. So if we write out the sum, we get eta mu 0 times x0 plus eta mu 1 times x1 plus eta mu 2 times x2 plus eta mu 3 times x3. However, because the metric tensor is a diagonal matrix, it means that only one of these 4 terms will survive. If we're considering x0 on the left-hand side, then only this first term will contribute. That's because eta 0, 0 is plus 1, whereas eta 0, 1, eta 0, 2, eta 0, 3 are all zeros. On the other hand, if I have x1 on the left-hand side, then only this term will contribute, because only eta 1, 1 is non-zero. Eta 1, 0, eta 1, 2, eta 1, 3, as you can see from the second row here, are of course all zeros, and so on. So you can immediately see what happens here. When I'm writing down the covariant 4 vector for the position on the left-hand side here, we're going to get an object that is almost exactly the same as the original contravariant 4 vector, but just with some pluses and minus signs. In particular, the time-like component is going to get a plus sign, and the space-like components are going to get minus signs. So when we put all this together, we can write our contravariant 4 position x mu as ct xyz, this is the 4 vector, whereas the corresponding covariant for position, because we do this contraction with the covariant metric tensor eta, we get Ct minus x minus y and minus z. So finally, we see that after all of this fuss, the contravariant 4-vector has time-like and space-like components in this form, Ct and a 3-vector r, whereas the corresponding covariant 4-vector simply has a minus sign on the space-like components, and that's really the only difference between the contravariant and covariant 4-vectors within the theory of special relativity in flat Minkowski spacetime. As I mentioned, things get more complicated in the curved spacetime of general relativity, but we won't be getting into that in this course. So the only thing we need to remember here is that the space-like components get an extra minus sign when we're talking about the covariant 4-vector. So now we're in a position to talk about the generalized dot products of 4 vectors. As we talked about in a previous lecture, this is basically the inner product of these 4-dimensional spacetime vectors. These are also called Lorentz scalars, which are a generalization of the usual scalars in our 3-dimensional Euclidean space. When we generalize to 4 dimensions, we also have the notion of a scalar. When we talk about a dot product being a scalar product for regular 3-dimensional vectors, we have the generalized dot product of our 4 vectors being a Lorentz scalar. And those are obtained simply by taking the inner product of our 4 vectors. So what does this mean in practice? Well, consider the following object. This is the contraction of 2 4 vectors. One of them is a contravariant 4 vector and the other is a covariant 4 vector. I say it's a contraction because we have a repeated Greek index mu here, one of them lower and one of them upper. So of course this object really means that we sum over mu. And of course now we can just write out component by component what this product corresponds to, because we know term by term the elements of our contravariant and covariant for position. Term by term we just get these 4 objects, and if we just plug in the actual values of these things, we see that this is equivalent to Ct squared minus x squared minus y squared minus z squared. The fact that we have one covariant and one contravariant 4-vector means that we get these minus signs here. We get a relative minus sign between the space-like components and the time-like components when we do this contraction. Notice that we can also write this product on the left-hand side here in terms of 2 contravariant 4 vectors, if we also include the metric tensor in our Minkowski spacetime, which is this eta. That's just following from the definition of our covariant 4-vector in terms of the contravariant one. So we can kind of see that this is basically just like a regular dot product of the 4 vectors, but because we've got this extra metric tensor in here, we get this extra minus sign on the space-like components. Whenever you see a contraction of 2 4 vectors like this, imagine that we're calculating the square modulus length of the vector, but in our 4-dimensional spacetime, because we have the Minkowski metric tensor encoding the underlying hyperbolic geometry of spacetime, we have this extra minus sign coming in. This is like the Pythagoras theorem, but generalized to 4th dimension, the 4th dimension being time, and entering here with this relative minus sign. Now, just as x mu is a given for position of a particular event, we can also take the difference between 2 4 vectors. By the property of linearity of our 4 vectors, we can then write delta x mu simply as the difference between our 4 vectors for 2 events A and B. In component form, we then just have the difference term by term for each component for event B and event A. We can therefore express this as c delta t, delta x, delta y, and delta z. These are the differences in the time coordinate and the x, y, and z coordinate between our 2 events. Importantly, because of the property of linearity, when we take these differences, we obtain an object that is again a 4-vector. Delta x mu is a 4-vector. And of course, we can do the same thing for the covariant 4 position. Therefore, if we write down the Lorentz scalar for these four vectors, then we see it is simply c delta t squared minus delta x squared minus delta y squared minus delta z squared. And we recognize from the usual three-dimensional Euclidean Pythagoras theorem that delta x squared plus delta y squared plus delta z squared is itself simply the distance between 2 points in space, delta r squared. This object is not a four-vector, it's a scalar. Furthermore, we see that here we've obtained the space-time interval. As we saw in a previous lecture, delta s squared, which we now know to be this Lorentz scalar object, is something that's the same in all inertial reference frames. It doesn't depend on the reference frame we're in, and it's invariant to the Lorentz transformations. We will see that emerging very naturally within this index notation involving four vectors when we consider the Lorentz transformations of four vectors, which we're going to do now. How does a four-vector x mu in a reference frame S look in a different reference frame S primed? We'll assume, as usual, that S and S primed are reference frames in the standard configuration, meaning that we have aligned axes and the origins coincide at t equals 0, and that there's a relative velocity between S and S primed in the x direction. If S is an inertial reference frame, then S primed is an inertial reference frame as well, provided that the velocity v along the x direction is constant. In that case, we know what the Lorentz transformations are, and indeed in a previous lecture we assembled these into a single matrix transformation. Now we're going to look at the four-vector version of the Lorentz transformations using the index notation. Generically, we have a Lorentz transformation that takes a contravariant for position x nu in reference frame S and converts it into a contravariant for vector x mu in reference frame S primed, which I denote using this primed on the left-hand side here. The object that performs this Lorentz transformation is this thing here, lambda, and it has one upper index, mu, and one lower index, nu. As before, we can think of a kind of rule of thumb, mnemonically at least, where we imagine cancelling these two indices nu here, and then that leaves us with a single upper index mu, which we then see on the right-hand side. So this is a little bit different from the contractions we've seen previously, which, for example, raise or lower the indices, or eliminate the indices altogether, as in the Lorentz scalar contraction. Here we see a transformation. We turn one contravariant four-vector into another contravariant four-vector, and we do that by contracting out this index nu here, and we're left with an index mu. Of course, this is just a mnemonic. We don't really cancel out these nus. We use the Einstein summation convention. We have a Greek index, one upper and one lower, and so really it is implied here that we sum over the four values that nu can take, 0, 1, 2, and 3, of this product. Following from the original Lorentz transformations, it's easy to work out what this object here, lambda, should be. In special relativity, it helps to regard this object lambda as an element of the matrix lambda here, with the double line underneath again to indicate that it's a matrix. The fact that we have one upper index and one lower index has a subtle meaning. We won't get into that here. We'll actually just regard this basically as an element of a matrix with a row mu and a column nu. And we can actually do this because the matrix lambda is again a symmetric matrix, meaning that it doesn't really matter which one we regard as mu and which one we regard as nu. It can either be the rows or columns and rows. In practice, when we're calculating these objects, it doesn't really matter. The Lorentz transformation matrix, lambda mu nu, is given by this 4x4 matrix here. This is specifically in the case of a Lorentz boost along the x direction. That means our two reference frames are connected by a relative velocity v along the x direction. Beta is therefore the relative velocity in units of the speed of light, v over c, and gamma is the Lorentz factor 1 over the square root of 1 minus beta squared. All of this was covered in a previous lecture where we derived all of these equations. The purpose of this lecture is to reformulate this physics in terms of four vectors in the index notation. Again, when referring to a row mu and a column nu of this matrix, because mu and nu are Greek indices which run over 0, 1, 2, and 3, we can label the rows and columns 0, 1, 2, and 3. 0, 1, 2, and 3. And when we pick a specific element of this matrix, we can therefore refer to it by its rows and columns mu and nu. So we have the Lorentz transformation defined in this way, where we have an implicit sum over nu, which contracts that index. It converts one contravariant 4 vector in a reference frame S to another contravariant 4 vector in reference frame S primed. The 4 vector in question is the 4 position here, Ct, x, y, z, and our Lorentz transformation matrix is this 4x4 object from the previous slide. So let's just show by brute force calculation that this expression here really is equivalent to our familiar Lorentz transformations. Let's try to calculate Ct primed in terms of quantities in the unprimed reference frame. Ct primed is, of course, x naught in the primed reference frame. X naught gives me Ct, and in the primed reference frame, I would get Ct primed. So this object is given by lambda 0 nu times x nu, and of course here we have implicitly the Einstein summation convention over the values of nu. And when we write out that sum, we get these 4 terms. That's really all this notation means. This is just a compact way of writing out all of this stuff. Now, we know x0, x1, x2, and x3 are just the 4 components of the 4 position in the unprimed reference frame, Ct, x, y, and z respectively. Likewise, we have components of the Lorentz transformation matrix lambda, where the first index corresponds to the row, the second index corresponds to the column. Again, we can just look up the elements of this matrix very easily. We need the 0, 0, the 0, 1, the 0, 2, and 0, 3 element of this matrix. So just substituting those values in, we have x0 is Ct, x1 is x, x2 is y, x3 is z. We have lambda 0, 0 is this component gamma. Lambda 0, 1 is this component minus beta gamma. Lambda 0, 2 and lambda 0, 3 are both 0. So actually, these last 2 terms don't contribute. Overall, therefore, we simply have that Ct primed is equal to gamma Ct minus beta gamma x. Or I could just write that by factorizing out this factor of gamma as gamma into Ct minus beta x, which is indeed the equation that we're looking for. That's correct. One can similarly repeat this procedure for x1, x2, and x3 in the primed reference frame, thereby obtaining the full Lorentz transformations. And indeed, we'd find that we would recover the equations that we'd previously derived. This is capturing the same physics, it's completely equivalent, it's just a different formulation, it's a different notation. 4 vectors are in fact defined as being objects that transform under the full symmetry operations of the so-called Poincare group. This involves 3 different types of symmetry operation. The first is translations, or displacements if you like, in space and or time. It basically means that we can shift the origin of our coordinate system through space, and also we can consider a different reference time to be our t equals 0. Together, this forms an abelian Lie group of translations on spacetime. Secondly, we have rotations in space, and actually these form a non-abelian Lie group. Finally, we have Lorentz Boosts. These are transformations that connect 2 uniformly moving bodies. The Lorentz transformations allow us to go from one inertial reference frame to another, moving at a constant relative velocity. The full group of these Lorentz Boosts corresponds to this 3rd symmetry category here. Taken together, the second 2 here, rotations and Lorentz Boosts, make the Lorentz group. However, the full symmetry of special relativity is the Poincare symmetry, which involves all of these symmetry operations. Lorentz scalars are objects which respect this Poincare symmetry. That means that they do not change when we perform translations or rotations, or we perform the Lorentz transformations. This, in turn, means that Lorentz scalars are the same in all reference frames. we refer to them as Lorentz invariants or relativistic invariants. So let's look in a bit more detail to these Lorentz scalars. These are objects which do not depend on the reference frame. So let's now consider two 4 vectors. Let's call them A and B. If these objects are genuine 4 vectors, then it must mean that they transform according to the Lorentz transformation. In that case, we can write down these two equations, one for A and one for B. We start off with contravariant 4 vectors in the unprimed reference frame, A nu and B nu, and then by contraction with the Lorentz tensor here, we're able to obtain the corresponding contravariant 4 vectors A mu and B mu in the primed reference frame. Provided that we have two such 4 vectors, then we can form the product A mu, B mu, one with a lower index, one with an upper index. This is a contraction because we see here the repeated Greek index, one lower, one upper, so we have implicitly the Einstein summation convention to consider here. We're summing over the different values that mu can take. So this is basically like the generalization of the regular dot product of vectors in 3D space to the 4 vectors in space-time. This is an inner product, and we'll see that it's actually a Lorentz scalar, meaning that it indeed is something that doesn't depend on the reference frame. Now, if that's to be so, then it means that this object, this product, should be the same in one reference frame as another reference frame. If I write these 4 vectors down in a given reference frame, as I have done here, A and B, then I can transform to a primed reference frame, a different reference frame, moving relative to the first one with a constant velocity v. And if this really is a Lorentz scalar, then these two objects should be the same. So let's prove this relation. And notice here that this is completely general. It holds for any two 4 vectors and for any two inertial reference frames. So how do we go about proving this? Well, we'll just take the left-hand side of the equation here and we'll substitute in our two expressions for these Lorentz transformations and thereby obtain something in the unprimed reference frame, and we can compare that with the right-hand side of the equation. But before we can do that, we actually need to convert our covariant 4 vector in the primed reference frame to a contravariant 4 vector in the primed reference frame. That's because the Lorentz transformation equation that I've written down here is for the contravariant 4 vectors, whereas in this equation we see that A appears actually as a covariant 4 vector. So I need to raise the index of this object first before we can proceed. That gives me this following form, where I've now converted the covariant A mu to a contravariant A nu, and again we assume that we're contracting over this Greek variable nu here. On the right-hand side, I'm writing the same product of our 4 vectors in the unprimed reference frame, but here I actually switched the dummy variable mu to the dummy variable alpha. So what do I mean by the dummy variable here? Well, mu and alpha don't actually feature in the end result. That's because it's a repeated index and I'm implicitly summing over it. So in this first expression, I implicitly have a sum over mu taking the values 0, 1, 2, or 3. In the second expression, I implicitly have a sum over alpha taking values 0, 1, 2, or 3. So whether I call that label mu or alpha doesn't matter. I'm still summing over specific values, and in the end, I get the same result no matter what I call the variable. So on the left-hand side, I've now simply inserted the Lorentz transformations for my A and B contravariant 4 vectors. In this first part, written in blue, I have a contraction over this dummy label sigma here, which leaves me finally with A nu in the primed reference frame. And for the red piece, we have the transformation of the B 4 vector. I see that from the contraction of this dummy index alpha here, I'm going to end up with B mu in the prime reference frame, which is exactly what I want. So on the right-hand side, to make the comparison, I have to raise the index of this covariant 4 vector, A alpha, and I'm going to turn it into a contravariant 4 vector, A sigma. And that will leave me with this expression. Now, I can tidy the expression up a bit on the left-hand side. Notice that these objects are not themselves matrices. They can be regarded as elements of matrices, but each one of them is in fact just a simple single scalar number. Therefore, I can rearrange these objects at will. And that leaves me with this expression. And so on the left-hand side and the right-hand side of the equation, I see the same factors, A sigma and B alpha. A sigma and B alpha. Both of them are contravariant 4 vectors with the same indices. So if this equation holds true, and therefore if the product A mu, B mu is actually a Lorentz scalar, then that implies that this factor here must be equal to this factor. So I have this expression, and in fact it's very easy to check that this equation is indeed satisfied. Let's just see that this equation actually makes sense. We have a lot of indices in here, and there's actually several summations implied. On the left-hand side, we have an implicit sum over the variable nu, and we also have a sum over the variable mu. These are both repeated indices. Mu is repeated, 1 upper and 1 lower, and nu is repeated, 1 upper and 1 lower. So really, we can write this thing as the double sum over mu and nu. After all of that, on the left-hand side, we're therefore left with 1 sigma and 1 alpha, and that's exactly what we see on the right-hand side of the equation here. Furthermore, with the explicit expression for the Minkowski metric tensor eta and the Lorentz transformation matrix lambda, we can simply verify that this equation holds. An easy way to do this is to recognize that on the right-hand side of the equation here, we basically have an element of a matrix, and on the left-hand side, we have an element of a matrix product. Mathematically, the equation in the box here is identically equivalent to saying lambda eta lambda is equal to eta, where lambda and eta appearing in this equation are now treated as matrices. So to prove this, we simply write out our matrix identity here and substitute in for the Lorentz transformation matrix here written in black, and the Minkowski metric tensor eta written here in blue. If you just multiply out these 3 matrices, you'll indeed find that we recover this eta on the right-hand side, where we have to remember that here gamma is 1 over the square root of 1 minus beta squared. With that identity and these matrices at hand, we can actually prove that this identity is correct. So the punchline of all of this is that if A mu and B mu are genuine 4 vectors, then this object, the contraction A mu, B mu, is the same in all reference frames. It's a Lorentz scalar. And this holds for any pair of 4 vectors. A and B could be any 4 vectors. They could also be the same 4 vector. In particular, the spacetime interval delta S squared, which is defined as this object, must therefore be a Lorentz scalar and is the same in all inertial reference frames. We saw in the previous lectures that this plays a very important role within the special theory of relativity. So we've now discussed at length the properties of one such 4 vector, the 4 position, which describes an event in spacetime. We have 4 coordinates, t, x, y, and z. But what about other 4 vectors? We've just spent some time to prove some general relations about relativistic invariants involving pairs of 4 vectors, but so far we've only identified one 4 vector. In fact, as we'll see, there's a whole family of 4 vectors. There's the 4 velocity, the 4 acceleration, the 4 momentum, the 4 gradient, the 4 potential, the 4 force. There's many different objects which can be assembled into 4 vectors and which transform according to Lorentz transformations. One way of generating these 4 vectors is to take an existing 4 vector and differentiate it. So let's start off with the 4 velocity, which is obtained from the 4 position by taking the time derivative. But here we have to be a little bit careful. What are we differentiating with respect to? We differentiate with respect to time, but time in which reference frame? Do we do d by dt, or d by dt primed in a different reference frame? What time do we differentiate with respect to if time itself is a relative quantity? If the 4 velocity u mu is going to be really a 4 vector, then it means it must transform according to the Lorentz transformations. Therefore, if we start out with the 4 position, which is a 4 vector, then we must differentiate with respect to something that is the same in all reference frames. In fact, the 4 velocity is obtained by taking the proper time derivative, d by d tau. Remember, the proper time is the wristwatch time to an observer at rest at the origin of his own reference frame. The proper time is a relativistic invariant. This can itself be seen from the relativistic invariance of the spacetime interval delta s squared. That's because delta s squared is equal to delta s primed squared in any reference frame, following from the fact that delta s squared is itself this contraction over these four vectors, and we've just proved that that object is relativistically invariant. Since delta s squared generically is defined as being c delta t squared minus delta r squared, then we could simply consider a different reference frame in which the observer was at the origin, at rest, in his own reference frame. The time coordinate in such a situation is the proper time, and since we're at the origin of our coordinate system, then delta r squared is equal to 0, and therefore delta s primed squared in this particular reference frame is simply c delta tau squared. This is when we're at the origin of our own rest frame. But since we've just established that delta s squared is the same as delta s primed squared, we note that in any reference frame, the spacetime interval is basically simply equal to c delta tau squared. So we've just proved that apart from this factor of c, the spacetime interval is actually equal to the proper time. And therefore the proper time is indeed also a relativistic invariant. What this means is that when I take the Lorentz transformation of delta s, or equivalently now delta tau, I get the same result. This implies that if I take the proper time derivative of the four position, this will again be something that transforms like a four vector. Why? Because the four position is a four vector, and we're taking the time derivative, the proper time derivative, which is invariant to the Lorentz transformation. So we define the four velocity u mu as d by d tau of x mu. This is then guaranteed to transform like a four vector. Using this relation that delta s is equal to c delta tau, I can actually also write this as simply c d by ds of our four position x mu. So let's evaluate this four velocity using this definition. First of all, we use the chain rule to write the proper time derivative, d by d tau, in terms of the coordinate time derivative, d by dt. Then we incur this factor of dt by d tau, and by the time dilation formula, we note that this object is simply the Lorentz factor gamma, which of course is a function of the relative velocity between our reference frames. Here we're talking about two reference frames, one measuring a time t and the other measuring a time tau. We have an observer in a given reference frame with a given time t, and then we have an observer at rest at the origin of their own coordinate system, and of course they're measuring the proper time tau. The velocity v is simply the relative velocity between these two reference frames. So by the chain rule, we can write that the four velocity u superscript mu, which is the contravariant for velocity, is given by gamma dx mu by dt, where t here is really the coordinate time. Now, since the four position x mu is itself given by ct, x, y, and z, we can actually now perform explicitly this differentiation with respect to the coordinate time t. So I will obtain that the contravariant for velocity u mu is the factor gamma multiplied by c times dt by dt, dx by dt, dy by dt, and dz by dt as the four components. This obviously gives gamma into c, and then simply the velocity components, the regular three velocity components, vx, vy, vz, along the x, y, and z directions respectively. I could also express this as gamma multiplied by the four vector which has components c in the time-like component, and then the velocity vector v in the space-like components. This v vector here is the regular, non-relativistic three velocity. This four velocity is a genuine four vector, and therefore it does transform according to the Lorentz transformations. meaning that I can write u mu in a primed reference frame and relate it in the usual way to u nu in the unprimed reference frame by performing this contraction with the Lorentz tensor. I can also consider the Lorentz scalar product given by this contraction. Again, of course, the Einstein summation convention over the repeated index mu here is implied. Following the usual rules, we can multiply this out. We would find that it is equal to gamma squared into c squared minus v dot v, otherwise known as c squared gamma squared into 1 minus v squared over c squared. Interestingly, this object can be seen to be exactly simply c squared. And that's because the definition of the Lorentz factor gamma is 1 over the square root of 1 minus v squared upon c squared. So this factor gamma squared out the front here cancels with this factor in the bracket, leaving us overall with a factor of c squared. Now, as emphasized on the previous slides, these Lorentz scalar products, things that look like this, involving the contraction of a contravariant and a covariant 4-vector, are the same in all inertial reference frames. So this object, this Lorentz scalar product, the value c squared here is something that is the same in all inertial reference frames. In fact, we could have got this result in a far simpler way. And this is actually a kind of teachable moment because this is a trick we often play in special relativity when dealing with these 4-vectors and contractions. What we can do is consider a specific reference frame. In particular, let's consider the co-moving or rest frame of a particle. We switch to a reference frame which is just moving along at the same velocity as our particle. In this rest frame, it looks like the particle has 0 velocity. In this primed reference frame, we would say that v primed vector is simply 0. I can now evaluate this object, this Lorentz scalar object here, in the primed reference frame. And I know that that object, because v primed is equal to 0 in the primed reference frame, must simply be equal to gamma squared c squared. That's because, by our definition of the contravariant for velocity here, we have gamma, c, and v. If v is equal to 0 in the reference frame S primed, then this component is just 0. When we perform the contraction, we're going to get a factor of gamma twice, a factor of c twice. We multiply those two things together, and we get gamma squared c squared. However, if we're in the co-moving rest frame, that means v is equal to 0, and so the factor gamma is actually also equal to 1 in this rest frame. So, overall, we find that this contraction is equal to c squared. But since these objects are the same in all reference frames, we know that c squared must also be the result when we consider it in any reference frame. And of course, this is the explicit result that we recovered by doing it for a general velocity v. So you see, this all works out. We will actually use this trick of evaluating these scalar products in specific convenient reference frames many times, and this is the first example that I wanted to provide of that technique. Let's now move on to consideration of the so-called 4 momentum. This is denoted by the 4-vector p mu. It has 4 components, and it's a genuine 4-vector that transforms under Lorentz transformations. It's simply given by the 4 velocity that we've just calculated, and that we know is a 4-vector, multiplied by the mass of the particle. And I'm giving specifically this mass here a subscript 0 to indicate that this is the so-called rest mass of a particle. I mean here it's the mass of a particle in its own rest frame. We'll see what that means and why that's important later. The rest mass is basically the object we would normally call the mass of a particle. This is a scalar quantity. All observers would agree what the mass would be in the particle's own rest frame. Because we take a 4-vector and multiply it by a scalar quantity, we obtain another 4-vector. So the 4 momentum, so defined, is indeed a 4-vector. The definition of the form momentum here makes the analogy clear between the regular non-relativistic momentum, which is just the mass times the velocity. Here we have the rest mass multiplied by the forward velocity. Often you will see this take the form mc in the time-like component and a vector p in the space-like components, where we define here m as the relativistic mass, meaning the rest mass m0 multiplied by the Lorentz factor gamma. Likewise, we have a regular three-dimensional vector p here, which is defined as being the relativistic 3 momentum. Not the 4 momentum, but the 3 momentum, and it's relativistic because again we see this Lorentz factor gamma appear. It's gamma times the rest mass times the velocity. So here m0v would be the regular non-relativistic 3 momentum. We multiply it by the Lorentz factor gamma and we obtain the relativistic version. So there's some kind of consistency in the notation here. We have m0 for the rest mass, we have m, which is gamma times m0, is the relativistic mass. We have m0v would be the non-relativistic 3 momentum, and then we multiply it by a factor of gamma, and we get the relativistic 3 momentum. We can assemble these things together into a single 4 vector. We multiply the relativistic mass by the speed of light, mc. That goes in the time-like component of the 4 momentum. And then we have the relativistic 3 momentum in the space-like components of the relativistic 4 momentum. So what is the physical meaning of the time-like component of the 4 momentum? P0 is equal to mc. Well, written out in full, we have that mc is equal to gamma m0c, which in turn is m0c multiplied by 1 over the square root of 1 minus v squared over c squared. This is the definition of the Lorentz factor gamma. This is the exact definition of the time-like component P0 of the 4 momentum. Let's now consider specifically the non-relativistic limit, where the velocity of the particle v is much, much less than the speed of light c. In that case, we know that v squared over c squared will be extremely small, and we can perform a Taylor series expansion of this gamma factor. We've done this a few times before, the result should be familiar by now. We see that we get this leading factor here, m0c, multiplied by 1 plus a half of v squared over c squared, and then higher order corrections, which are actually of order v upon c to the power of 4. So if v is much, much less than c, then v over c to the power of 4 is extremely small, and those are the terms we're going to neglect in the non-relativistic limit. If I now multiply both sides of the equation by an additional factor of the speed of light c, on the left-hand side I would get mc squared. On the right-hand side I get m0 c squared plus a half m0 v squared, and then there would be some higher order corrections here which are beyond the non-relativistic limit, which I'm neglecting. This is an extremely interesting equation. On the right-hand side here we see a factor half m0 v squared. This is precisely the non-relativistic expression for the kinetic energy of a particle. In the non-relativistic world, m0 is literally just the mass. We don't have any concept of a relativistic mass there. So a half m0 v squared is, of course, the non-relativistic kinetic energy. The dots here, representing the terms that we neglected, are therefore obviously the relativistic corrections to this kinetic energy. All of the neglected terms here have at least a factor of v squared, with v the velocity, and they have units of energy. For this equation to be dimensionally correct, that implies that these other two terms are also energies. They have units of energy. Now, if we consider a particle at rest, where the velocity is equal to 0, then obviously the kinetic energy, a half mv squared, is equal to 0. Therefore, mc squared here is equal to m0 c squared when we're at rest. And this can be regarded as a rest energy. This object has units of energy, and since the particle is at rest, there is no kinetic energy. m0 c squared can therefore be regarded as an intrinsic rest energy of the particle. It only depends on its rest mass, which is the same for all observers, and the universal constant c squared, which involves the speed of light. Again, this is something that is the same to all observers. So the quantity m0 c squared is a relativistic invariant. It's the same to all observers. It is also a significant contribution to the overall energy. That's because the speed of light c is so large. If we imagine 1 kilogram of mass, the equivalent rest energy would be 25 million kilowatt hours. That's a lot of energy. And of course, this is at the heart of all nuclear power generation. So, the total energy of a free particle, and what I mean by free particle here is that it's one that's not subject to any potential, it's simply moving around in free space. The energy of a free particle is clearly this intrinsic rest energy when the velocity is equal to 0, plus the kinetic energy of the particle, which accounts for the contribution to the energy when v is not equal to 0. In the non-relativistic world, this is simply a half m0 v squared. That's the kinetic energy for non-relativistic physics. The relativistic corrections to the kinetic energy I will again represent by these dots here. So what we've identified here is that this whole object is equal to the total energy of a free particle. It consists of an intrinsic rest energy, m0 c squared, plus a non-relativistic kinetic energy, plus the relativistic corrections to the kinetic energy. Overall, this is the total energy of the relativistic particle. And all of that stuff is actually equal to mc squared, where on the left-hand side of this equation, m is the relativistic mass. Overall, therefore, we've derived that the total energy E is equal to mc squared. This is Einstein's famous mass-energy relation. This equation is true in all reference frames. We have to just bear in mind, however, that the m here is the relativistic mass. So if we are in a given reference frame and we see a particle moving by with a given velocity v, then the total energy can be written as mc squared, where m is m0 gamma c squared, and the gamma here is, as usual, 1 over the square root of 1 minus v squared over c squared, and v is the velocity of that particle. So the energy here depends on the speed of the particle. It also depends on our reference frame. The v appearing in this equation that enters in the gamma factor here is the relative velocity between us and the object. So what we see here is that the energy of a particle depends on the reference frame. It is not itself a relativistic invariant. m0 c squared, which is the rest energy, the intrinsic rest energy, is a relativistic invariant. mc squared, where m is m0 gamma, the relativistic mass, is something that depends on the reference frame. This object is the energy of the free particle in a given reference frame. This equation, E equals mc squared, is of course a very famous equation and is key in determining the physics of relativistic kinematics. We can now use these definitions of the four-momentum and Einstein's mass-energy equivalents to derive an even more powerful and general formulation called the energy-mass-momentum relation. This will be the fundamental equation of relativistic kinematics, and we'll see that it's extremely useful when doing actual calculations in relativistic mechanics. The first step is to note that we can identify the form momentum either as mc in its time-like component, or, using Einstein's mass-energy equivalence, we can write this as E over c. And again, in the space-like components, we have the relativistic 3 momentum as before. Since we've identified the 4 momentum as a genuine 4-vector, this of course implies that we can perform a Lorentz transformation on it using this usual formulation. We can therefore transform the 4-vector from one reference frame to another. In particular, we can transform to the rest frame of a particle in which the velocity v primed is equal to 0. This implies that the relativistic mass m is actually the rest mass, because we're in the rest frame, and also the relativistic 3 momentum p vector here is equal to 0, because our velocity is equal to 0. In the rest frame, therefore, we can write the relativistic 4 momentum p mu primed as m0 c in the time-like component and 0 in the space-like components. And equivalently, we can write that as the energy E over c in the time-like component, but in the rest frame, we'll call this the rest energy E rest. Again, we have 0 in the space-like components. This is just following from these two equations. In particular, note that the energy E and the relativistic 3 momentum, P vector, both depend on the reference frame. They are not relativistically invariant. They are components of a 4 vector, they're not a 4 vector themselves. On the other hand, the Lorentz scalar, formed by making the contraction of the contravariant and covariant 4 momentum, is a relativistically invariant object. It's the same to all observers in different reference frames. According to the usual rules for making these Lorentz scalars, if I have a 4 vector which is of this type here, drawn in red, then I obtain E upon C squared for the time-like component, and then minus P squared for the space-like components. The minus sign coming in here because we have one covariant and one contravariant 4 vector. On the left-hand side of the equation, I'm computing the same object, but in the rest frame of the particle. Then I will use this expression for the relativistic 4 momentum in the rest frame, and in this case, the Lorentz scalar is a very simple object. It's just m0c squared. That's because the space-like components are equal to 0. So here we've utilised the relativistic invariance of these Lorentz scalars to derive this interesting equation. After some small rearrangements, we then end up with this expression, that E squared is equal to P squared C squared plus m0 squared c to the 4. This is just rearranging this expression a little bit. And this is referred to as the fundamental equation of relativistic kinematics. It relates the total energy in a given reference frame, E, to the momentum in that reference frame, P, and the rest mass, m0. In the next lecture, we'll be utilising this expression extensively when we're studying relativistic mechanics. Let's consider now a quick example of a photon. The 4 momentum, as usual, the contravariant 4 momentum, we'll define as E over C in the time-like components and the relativistic 3 momentum P in the space-like components. Interestingly, in the case of photons, we have that the mass is equal to 0. Photons are massless particles. However, they still have a momentum. From de Broglie's equation, we know that the wavelength of the photon, nu, is given by the speed of light c times the momentum p divided by Planck's constant h. And of course, by the Planck-Einstein relation, the energy of the photon is related to h times that frequency, nu, which is therefore equivalent to the speed of light times the momentum. This implies that for our massless photons, our 4 momentum, p mu, can actually be written simply as p in the time-like component and p vector in the space-like component. Notice that this is perfectly consistent with the energy-mass-momentum relationship that we've just been discussing, which for a massless particle would imply that E squared is equal to P squared C squared, or that E over C is equal simply to P. So these equations are actually consistent. Here, P is of course just the magnitude of P vector, and P vector, as before, is the relativistic 3 momentum. One interesting consequence of this is that when we form the Lorentz scalar product, involving the contraction of the contravariant 4 momentum and the covariant 4 momentum, we actually simply get 0 for this product. And being a Lorentz scalar, this product must be equal to 0 in all reference frames. Let's ask ourselves now, how does the frequency of the photon nu appear to a moving observer? Well, let's transform to a moving reference frame, which will be the primed reference frame. We do this using the usual Lorentz transformation, as I've written down here. Let's consider specifically the time-like components of the 4 momentum in the primed reference frame. That's p0 primed, and therefore I use mu equals 0 in this expression. I have an implicit sum over sigma, and then I obtain on the right-hand side of the expression gamma p0 minus beta gamma p1, involving components of the 4 momentum in the unprimed reference frame. What I've written down here is explicitly the expression for a Lorentz boost along the x direction. In a given reference frame, we observe that the frequency of the photon is nu. This is the unprimed reference frame. Now, we adopt a different reference frame for our observer. This is the primed reference frame. which is moving along the x-axis with a relative velocity to the unprimed frame, and the relative velocity is a constant v. P0 is equal to the magnitude of the total relativistic 3 momentum, p, whereas P1 is the x component of that vector. Let's say our photon is also moving along the x direction. We're shining our light along the x-axis. In that case, the momentum only has an x component, and so the magnitude of the 3 momentum, p, is actually equal to px. Then we can factorize this expression, and we obtain this. In this case, we end up with our final result that p primed in the primed reference frame is equal to gamma into 1 minus beta times p in the unprimed reference frame. We can now convert this into frequencies by using the de Broglie relation up here, in which case we obtain that the frequency in the primed reference frame to the moving observer, nu primed, is equal to the frequency in the unprimed reference frame, nu, divided by this factor d, which is called the Doppler factor. D is just 1 over gamma times 1 minus beta, and a little bit of rearrangement, and also using the definition of gamma as 1 over the square root of 1 minus v upon c squared, gives an explicit expression for the Doppler factor, which is the square root of 1 plus beta over 1 minus beta. This is referred to as the relativistic Doppler effect. If I have some light shining along the x-axis, and I am an observer also moving along the x-axis, then the frequency of the light appears to change by a specific factor arising from special relativity, which is this factor here. It's the relativistic Doppler factor. Analysis of this equation tells you that if you are moving towards the light, if the light is oncoming, this corresponds to negative beta. Then we have a blue shift. The frequency is increased towards the blue side of the spectrum, whereas if we're moving in the same direction as the light, then we have a positive beta, and we have a red shift in the Doppler effect. This corresponds to the frequency decreasing. The colour of the light to the moving observer appears to be shifted towards the red end of the spectrum. So let's now consider some other 4 vectors, the 4 acceleration and the 4 force. First of all, we had the 4 position x mu, and from it we obtained the 4 velocity u mu. We did this by taking the proper time derivative. We had to take the proper time derivative rather than just a general coordinate time derivative, because we want this object to be a 4 vector, and therefore we want it to be able to transform according to the Lorentz transformations. If we start off with the 4 position x mu as a 4 vector, then we need to differentiate with respect to something that is the same in all inertial reference frames, and the proper time is such an object. In an exactly analogous fashion, we can define a 4 acceleration by taking the proper time derivative of the 4 velocity. We can also express that as gamma times du mu by dt for a general coordinate time t. We also considered the 4 momentum p mu, which was obtained from the 4 velocity by multiplying by another Lorentz scalar, which is the rest mass m0. We can therefore define a 4 force as the rate of change of the 4 momentum, but again, we have to take the proper time derivative of the 4 momentum for this to be a valid 4 vector. And therefore, we have a relativistic version of Newton's second law, which relates the rate of change of the 4 momentum to the 4 acceleration. This tells us that F mu is equal to m0 a mu. And this equation allows us to relate forces on particles to accelerations of those particles within special relativity. We'll be discussing more on this in the next lecture on relativistic mechanics. What about relativistic calculus? How can we take derivatives of 4 vectors? Well, if we start with the 4 position, which has components ct, x, y, and z, then of course we can take derivatives with respect to each of these components. Let's assemble those into a 4 vector. This 4 vector will be called the 4 gradient. The 4 gradient will look something like this: 1 over c d by dt, d by dx, d by dy, and d by dz. In the time-like component we have 1 over c d by dt, and in the space-like components we have the usual 3 gradient, which is denoted by this nabla vector symbol here. It might be surprising at first glance to realise that this object is actually a covariant derivative. I'll denote that with the differential operator d and the lower index mu here. So as defined, this is actually the covariant 4 gradient. This might be surprising because usually we expect the covariant versions of the 4 vectors to have a minus sign on the space-like components relative to the time-like component. So why am I defining this one with all the positive signs as being the covariant version of the 4 gradient rather than the contravariant one? Well, to understand that, consider a function which is going to be a function of our space-time coordinates t, x, y, and z. According to the fundamental theorem of calculus, I can write a small increment in the function df in terms of a small increment along our independent coordinate directions dt, dx, dy, and dz. And the factors here are the partial derivatives of the function with respect to those coordinates, df by dt, df by dx, df by dy, df by dz. If f is a scalar function, then obviously df must also be scalar. That means that I should be able to write it in terms of a contraction of a covariant 4 vector and a contravariant 4 vector. Here we have a total differential for our 4 position, dx mu, which is of contravariant type, and the covariant 4 gradient of our function f. Since we have a repeated index mu here, one lower and one upper, we have implicitly the Einstein summation convention, which means we contract this and obtain a scalar. This Lorentz scalar, when you multiply it all out using these definitions here, is precisely this expression here for the total differential df. So this implies that because I have a relative plus sign between each of these components when I write down the fundamental theorem of calculus, which gives me the increment in df, this tells us that indeed this differential operator here should be of the covariant form. Once we have the covariant form of the 4 gradient set, we can then easily obtain the contravariant 4 gradient. This is the differential operator d with a superscript mu here, that's the index in the upper position, and this implies that we should have the relative minus sign here. So it seems that for the 4 gradient, the contravariant and covariant gradients are the wrong way round, but all that's important is that we have a relative minus sign from going from contravariant to covariant, and that's what we have in these expressions. As a good mnemonic, you can think of the 4 gradient as having the index downstairs because we're differentiating with respect to the coordinates and they are downstairs in this expression. That's not really what's happening, but it's a good way of remembering the result. A particularly interesting quantity is the Lorentz scalar formed by contracting the covariant and contravariant 4 gradients. This is given the special symbol box squared, and you can see it's this Lorentz scalar object. When we do the contraction of these two things that I've written down here, we get 1 over c squared times d squared by dt squared minus the regular 3-dimensional Laplacian in space, this nabla squared. This whole thing goes by the name of the D'Alembert operator, and it's something that features very prominently in special relativity when doing mechanics problems, actually especially in the theory of electromagnetism. This D'Alembert plays the role of the Laplacian in regular mechanics. It's an operator corresponding to the second derivatives of our space-time coordinates. However, because it's formed by this contraction here, it's a Lorentz scalar, it means it's the same in all inertial reference frames. So here we have a differential operator that is the same in all inertial reference frames. In particular, you might notice this expression from the wave equation for light, and that's, of course, no mistake. This operator entering in the wave equation for light should be the same in all inertial reference frames because light propagates with the same speed in all inertial reference frames, and we get the same wave equation in all reference frames. So indeed, this operator should be something that is independent of the reference frame we choose. Finally, as an interesting example application of all of this, I want to consider the case of the classical theory of electromagnetism. Here we have another kind of 4 vector, which is called the 4 potential, A mu, and it has the scalar potential in the time-like component of this 4 vector, and the vector potential in the space-like components of this 4 vector. The reason why this is a 4 vector and the fact that it transforms correctly according to the Lorentz transformations is beyond the scope of the current lectures. However, I have a whole lecture series online on classical electromagnetism where I go into the relativistic formulation, so the link to that lecture will be in the description to this lecture. Check that out if you want to hear more. For now, we'll just take it as read that we have a 4 potential A mu. Now, let's consider the mechanics of a single charged test particle in an electrostatic potential phi. Here it's important, in this first part, that we consider an electrostatic potential, a potential that is not changing in time. We can write down the Lagrangian for this particle, L, which involves a free piece defined in the absence of any potential, and then minus the potential of the system. In the non-relativistic world, the free Lagrangian here would just be the kinetic energy. However, as we saw in the earlier lectures, in the relativistic case, this L free is minus m naught c squared into 1 minus v upon c squared. And if we have a charged particle in an electrostatic potential, then this potential u here is simply the charge q times the potential phi. The action, therefore, is the integral of the Lagrangian dt, and we'd obtain this expression. Importantly, in the second term here, we see minus q, the integral of phi dt. It's important to emphasize here that this holds in the electrostatic situation, when we don't have time-dependent electric and magnetic fields. That's important because it basically pins us down to a specific reference frame. It's the reference frame where the electric potential phi is at rest. If we adopt a moving reference frame, then the potential will appear to be changing, and this then is not the electrostatic situation that I want to consider here. So it's perhaps not too surprising that the action that I've written down here is not a relativistic invariant. However, if we think about the principle of least action and the principle of relativity together, then this implies that the action really should be a relativistic invariant. It should be something that is the same in all inertial reference frames. Why is that? It's because when we use the principle of least action, we minimize the action to find the correct classical path. The principle of relativity tells us that observers in different reference frames must all have the same physics. Therefore, different observers in different reference frames, when they're minimizing the action, should all pick the same minimum path if they're to get the same physics. In turn, this implies that the action should be relativistically invariant, so that they all choose the same minimum path. If the action was frame-dependent, then different observers might choose different minimum paths, and therefore they would get different physics. So when we take together the principle of least action and the principle of relativity, we're forced to conclude that the action has to be the same in all inertial reference frames. This means that the action should be made from Lorentz scalars. We know that these are the objects that are relativistically invariant. A valid action, therefore, would comprise terms that are Lorentz scalars, obtained by contracting 4 vectors. The problem with the action that we've written down here in the electrostatic case is that this is not a contraction of any 4 vector. This is not a Lorentz scalar object, and we have no right to expect that this action that I've written down here would indeed be the same in all inertial reference frames. And in fact it's not. So can we argue what the relativistic action should be for a charged particle subject to an electromagnetic potential? We have to come up with something that is manifestly relativistically invariant and is made from Lorentz scalars. To do this, we actually get a hint from the electrostatic case, which I've written down here. Here we have phi times dt. Now phi is the time-like component of the 4 potential, whereas dt here is the time-like component of the differential corresponding to the 4 position. So let me write these down. First we have dx mu, the contravariant 4 vector, and that has components c dt, dx, dy, and dz. Now I'm going to write down the covariant 4 potential, a mu, and that has components which I can deduce from the contravariant 4 vector over here, 1 over c times phi in the time-like component, and then minus the x, y, and z components of the 3 vector potential, minus ax, minus ay, minus az. I can now form a relativistically invariant Lorentz scalar product here by taking the contraction of these two 4 vectors, the covariant 4 potential and the contravariant differential dx mu here. This would give me the following components: phi dt minus ax dx minus ay dy minus az dz. And we recognise that in the action we have just the first of these 4 components. We have phi dt appearing, but we don't have these other components. To make the action a relativistically invariant quantity, we cannot just have phi dt on its own. We need to supplement it by these other 3 terms as well. We only saw phi dt in the electrostatic case because it only involves the electrostatic scalar potential phi. But in general, of course, we have also magnetic components corresponding to the vector potential A, and therefore we need to include these contributions from the magnetic vector potential as well. The argument that the action must be a relativistic invariant tells us the form in which the scalar potential and vector potential must enter into our action. We conclude that the action should involve the following terms: minus q integral phi dt, plus q the integral of ax dx, plus q integral ay dy, plus q times the integral of az dz. Overall, these 4 terms here can be lumped into this single term, minus q times the integral of a mu dx mu. And this is manifestly a Lorentz invariant object that is going to be the same in all inertial reference frames as we require. Notice also that when we go to the electrostatic limit, we just recover this first term, which is what we started with. This implies that we have a relativistic electromagnetic Lagrangian with this u here, this generalized potential u, being q times phi, the scalar potential, minus a, the vector potential, dotted into the velocity of the particle v. How did I get this formula? Well, the action is defined as the integral of the Lagrangian dt. So I need to pull out a common factor of dt from each of these expressions. The first one, phi dt, already has that, but the last 3 terms here are not in the form integral of something dt, and so it's hard to identify straight away what the Lagrangian actually is. So what I'll do is simply multiply and divide by dt in each of these terms, and recognise that dx by dt, dy by dt, dz by dt are the velocities of the particle along the x, y, and z directions. Then I have these terms, which have a common factor of q times the integral of something dt. If I analyse what's inside the integral there, I have a piece which goes as phi, I have an ax vx, ay vy, az vz. I can collect up these last 3 terms as the regular dot product of 3 vectors a dot v in here. So overall, I have a relativistic electromagnetic Lagrangian, which must be of this form, involving this generalized potential u. As I emphasized in the beginning of the course, this is interesting because it's a generalized potential which is actually velocity dependent. So this is slightly unusual. However, if we plug this into the Euler-Lagrange equations of motion, then it generates for us automatically the Lorentz force law, which tells us how the force on a particle relates to the electric and magnetic fields. So indeed, this is the ultimate verification that this formulation works. And so what we've learnt here is that because the action has to be a relativistic invariant quantity, the same to all observers, it implies a certain structure to the kind of Lagrangians that we can write down. In particular, the action can only be formed from pieces which are themselves Lorentz scalars, and as we saw, these are basically contractions over 4 vectors. In the particular case of electromagnetism, the part of the theory which involves the coupling of charges and currents to the electromagnetic fields is basically given by this term here, and the corresponding Lagrangian involves this generalized potential. So all of this was by way of a non-trivial example of the application of the four-vector theory to electromagnetism. So that's basically everything that I wanted to cover in this lecture on four vectors. In the next lecture, we'll be seeing how we can use some of this formalism to do actual mechanics problems. We'll be doing relativistic mechanics in the next lecture.